Oi, what is good, y'all? Today we are doing our first actual Triton kernel full tutorial, right? We're gonna go over what are we doing today? Well, we're gonna hit, of course, just the basics of Triton kernels as well as how to test and benchmark them, right? What you really need to get going. First up, importing PyTorch. Of course, that's a requirement. If you don't know what that is, we should have it all installed up and running, as well as Triton. I think I'm on Triton version 3.2 right now. Not that it should matter too much, but I do find it buggy enough. Make sure yours is updated. And then Triton.language, which we are going to call TL, right? That's what we actually end up using most of the time within the kernel, whereas the just Triton tends to be outside the kernel. And then we want our actual device. You can see here, if we do NVIDIA SMI, I currently have a 4060 Ti that I am SSH'd into, and we got to make sure our code knows what device we have. So torch.device, and this is a weird way to grab the device. Honestly, I forget why I was originally doing this. Whatever line you usually use to grab your device, whether it's CUDA, AMD, whatnot, should actually work just fine. I honestly forget why I'm using this line specifically to grab my device, but O equals. But to start off, let's build our actual test, right? So we're going to define a function. We can call it test add kernel. We're going to do an addition kernel here, addition of vectors. And it takes as input the size, which I think should be a tuple, but we'll see in a bit. Our absolute tolerance, meaning our Triton kernel is not going to give the perfectly exact same values necessarily compared to the actual PyTorch equivalent. And we have to say, all right, how much error can we tolerate in absolute terms, as in just subtract one from the other, and then absolute value it, as well as relative tolerance, which relative meaning, oh, some numbers are going to be relatively large, like a 1.2 or something, some very small, a 0.0006 or something like that, right? Absolute tolerance of 1e negative 3 would not work as well for those small numbers, so relative tolerance accounts for that better. And then we're going to set the actual device that our tensors go on as device, right? First up, we have to create the actual test data, and we're going to set our seed just so that we can replicate this. Not that it really matters per se replication-wise, but it's good practice that I usually forget to do to make sure people can actually replicate your code exactly if you have a weird error that's dependent on the actual random data, just in case. And then our first tensor x, torch.random normal distribution of shape size and on our device. Then our next tensor, these are going to get added together. Also a torch.random normal distribution, exact same parameters. And now we are going to run our Triton kernel and the PyTorch equivalent. So we're going to say the output is z, and z Triton equals add x comma y. We have not yet defined the add function. We'll do that in a bit. We're going to define that above our test kernel. And then z reference is x plus y. That is whatever PyTorch already has built in, right? And then we want to compare them and see if it's correct. And we do torch.testing.assert close z Triton and compare it to z reference or PyTorch reference. Absolute tolerance equals atol. Relative tolerance equals rtol. Right? What I like about using torch.testing.assert as opposed to a regular assert just built into Python is that this actually tells you what percentage of the entries are incorrect, if there are any at all, right? Meaning that oftentimes you can tell from the percentage, is my kernel just way off, or is there just like a very tiny little error that might have to do with a relatively small error? You might be able to tell something about your errors based off what percent of the entries are actually incorrect in the two tensors. And then if that does not throw up an actual error, we can just print passed, right? So that is our testing function. Next up, above that, we're going to define the add function, our actual wrapper around our kernel. This is not our kernel yet. This is just a function that takes in our input data and prepares it for our kernel. So define add, takes as input x and y, which are both tensors, PyTorch tensors. And we need to pre-allocate the output, right? Meaning that the tensor for the answer for z has to exist before we actually call our kernel, because our kernel needs to know where it's going to write the data to, right? So output, I could have called this z as well, I guess it was called z over in the test, but whatever, equals torch.empty like x. We can do an empty like here because it is the case that output is the exact same shape and everything else, data type, whatever, as x. But sometimes in more complicated kernels, in our future lessons, you will not be able to use empty like. You'll have to use empty and define your shape and define your data type and your device and all that, right? Now, I'm not going to do everything in terms of catching edge cases and assertions and making our code safe, but just here as an example, we might want to check that the tensors are on the same device. In reality, for your implementation wrapper functions, if you're going to actually use them like in deployment, you're going to need a whole bunch of assertions and everything. Obviously, you want safe code. But here we're going to just do a simple one, x.device equals device and y.device equals device, right? There's other like shape assertions, all that stuff. We're staying very simple for this lesson just because I'm not going to get bogged down in things that are less important when I know that our test case is not going to throw up those edge case errors, right? Now, here is the first big concept, is defining our launch grid. This is the actual number of kernel instances, number of programs that will run in parallel, right? So when we call a kernel, it doesn't just run the code once, it runs the code hundreds or thousands or tens of thousands of times, all in parallel across different SMs on the GPU, right? Sometimes multiple per SM. And we need to define how many of those to call and how to differentiate them, like, right? So what it is actually, it starts off as just an inline function here. It takes the input meta, but in reality, what we could do if we wanted a simpler one, it's just a tuple of numbers, right? M, N, whatever. What we want grid to be is a tuple. That's the important thing. A tuple whose entries are either one entry, two entries, or three entries, right? We could have also done a P or something, or just M. Those are all fine. We have not defined M yet, obviously. We want a tuple, though. And these entries have to be integers, okay? But we don't actually know what the inside entries are going to be yet, so that's why we're going to do an actual inline function that can help us determine that. Meta as in meta parameters, but name it whatever you want, I suppose. And then we are going to do a Triton function is ceiling division. What we want is the number of elements in our tensors divided by this hyperparameter or meta parameter, sorry, that we call block size. So the actual input to this is a dictionary. That's going to be true in general. But what is n elements? N elements is just either x or output, doesn't matter which you do. Dot numal, that's just a built-in PyTorch function, gives us the actual total number of entries in that tensor, total number of numbers in the tensor, right? And then, so we have n elements, and we are doing ceiling division by block size. We do not know block size yet. We'll actually just choose it arbitrarily here in a minute. It's going to be 1024. So let's say if our n elements had 4096 is the number of elements in X in output, right? Then it would be 4096 ceiling division block size, 1024. Therefore, you'd have 4 total. This would be a tuple that is just 4, right? However, to clarify what is ceiling division, cdiv of m and n, just any arbitrary input variables, is m plus n minus 1, and then all of that floor division by n to give us an integer, right? The point of this being that what if the number of elements in our tensor were not cleanly divisible by our actual block size, right? So I just said a second ago, our example was 4096 for n elements and 1024 for block size. Again, conceptually, we'll go over block size later as to what it is, but 4096 divided by 1024 is an easy division, but sometimes you might have 4097, right? In which case, block size does not cleanly divide 4097. You have one left over, a remainder. Ceiling division allows you to account for your remainder by instantiating by an actual kernel, a program, for that little remainder part that doesn't actually take up a full block size number of elements, right? And so once you have our actual launch grid, right? So this grid now defines how many different programs, different instances of our kernel are actually going to get called up. We can call our actual kernel, which we're going to define as add kernel, right? And it's not just a function. You actually, before you call the function, you subset or you index out that function using your launch grid, right? And then you treat it as a function. As inputs, we'll put in x, y, the output, the number of elements, and block size. But we're going to actually just define it right here. This is a heuristic we're defining. I'm just going to choose this number kind of arbitrarily. In general, with all meta parameters, which block size is one of, and we'll go over more of them later, you want to choose probably powers of 2, make things better. At the very least, in block size's case, you at least want a multiple of 32, given how warps work as discussed in our second lesson. But we'll get into more on this later. In future kernels, you will not have to actually define block size on your own. You want to set up any number. You'll actually have a way to have the kernel choose block size on its own, right? But for now, we're just going to set it to equal 1024. And so this actually calls the kernel. Notice we don't have any kind of output equals thing here. It just calls the kernel, right? That's because add kernel is going to write onto the entries of output in place, right? So once this gets called, output will have been changed and it will have been given the actual good output. And then we just return output. So now anytime you put in 2 tensors right here, it can give you the answer of addition, right? We still have to define our actual addition kernel. We have not done any actual Triton yet, right? And then you can see here, as you'd expect, remember, we defined add earlier, adding x and y together, and it should give us the same results as PyTorch equivalent. Now let's define our actual add kernel. So what we do is we don't just define a random function. We start off with triton.jit. This just tells Python that actually add kernel is not a regular function. It is a Triton kernel. Therefore, do not treat it like a Python function, right? So the decorator tells Triton and tells Python that we should actually compile this function on the GPU, not in Python's regular compilation scheme. As inputs, we're going to have x pointer, y pointer, and output pointer. Notice how I said pointer and not x, y, and output just plain, right? What actually happens is the fact that Triton is doing weird stuff on the back end to our kernel means that we don't actually get the original x. What we get instead is a pointer to the first entry, the first actual number in the tensor x, right? Same with y and output. These are not the full tensors. These are just pointers in memory to the place where the first entry of x and y and output actually lay. Then we do n elements as our next piece of input. N elements is just an integer. Remember, it's the number of total actual numbers in our tensor, and that doesn't get messed with. That's still just a number. And then block size, we're going to add on, it is of type tl.constant expression. What this means is it's telling Triton, hey, this argument is actually not going to change a whole lot. This is a compile time argument. You can know this at compile time, meaning it's static, right? So if this, the Triton can expect this to always be the same, basically. Once it, when it actually creates the low-level code, all the assembly CUDA, whatever, for our GPU kernel for us, it's going to take this number as a given and as a constant, whereas all of these numbers could change all the time throughout use. And meaning that every time you actually do change this number, if I were to call this function and then call it again, but this time with a different number, like 2048 or something, it would actually create an entirely separate kernel. Like when it actually turns our Python code into low-level ones and zeros, and assembly and whatnot, anytime you change block size, it's actually going to create an entirely separate kernel. So anytime you have values that you know are going to be very, very constant and that the kernel cares a lot about, then you're going to want to actually do this to make sure that it knows, hey, you can be extra efficient and just create a kernel that has this as a given, as a constant, right? It'll make more sense later when we get into actual using more than one meta parameter, more than one constant expression. But for now, we will explain that block size like that and elaborate on it more as we go on to future lessons. Now, first thing we do once we have actually begun our kernel, is remember there's many instances of this same function, of this same kernel being called all in parallel, right? Any given one instance needs to know, well, which one am I? Like, meaning, which chunk of the actual data is it my job to calculate, right? To get this, we do tl.program ID and then axis equals 0. Axis 0 referring to the grid, right? Remember our example here was our launch grid was, oh, I forgot a comma here earlier, it seems. Look at that. Fixing bugs already. So our example earlier of a launch grid of 4, basically axis refers to every single entry in this launch grid. There's only one here, so there's only one axis, axis 0. But then the PID, the program ID, is some number from 0 to 4 not inclusive. So meaning 0, 1, 2, or 3, right? This PID value, given this example, is going to be either 0, 1, 2, or 3, meaning each of those different PID values, it is their job to calculate using a different chunk of the data, right? So for example, if we had a vector of length 256, and if we had a block size of 64, then PID 0 might process elements 0 through 64, and that's Python like indexing here, so not actually including 64, it's 0 through 63. And then PID 1 might process elements 64 through 128, right? I say might because we have to actually, as we go down, define how we're going to use PID. But as an example, each PID processes different elements in the actual input or output, right? Same thing for this kernel because addition is very simple, just entry wise. Now, what we do first is the first step in using our PID to define which actual chunk, which block of elements we're going to process is we need to figure out, well, for whatever block we have, where do we start? So block start equals PID times block size, right? So our actual block size is 1024, as we said earlier, but like if it were 64, right? Then this is saying 0 times 64 for PID 0, 1 times 64 for PID 1. Therefore, in the case of PID 1, this would be that first little piece of the pointer, but we do not yet have the actual full indexing logic done, right? What we do next, what we need to figure out how long of a range this is and to get this indexing type behavior. The way we actually do that is we create an array of offsets, which are equal to block starts, so they start here, plus tl.arange 0 block size. This piece of code right here, this tl.arange, creates an array or a vector or whatever of int32 values, so just integers, right, of length block size from 0 to block size, right? So if you can imagine if our PID is 0, our block start would also be 0 because 0 to 64 is 0. And then this is 0 to 64. Add these two together, and our offsets would then be an array of numbers 0 up to 64, right? And that defines the actual entries in the original tensors that this specific instance of our kernel, that this program is going to process. What we do next is we actually load our data from DRAM, aka VRAM, aka HBM, high bandwidth memory, aka like global GPU memory, right, to SRAM, aka on-chip memory, right? There's just different names of the same thing. So we want to get our chunk of X. I'm going to call it X, but it is actually a block, a kind of chunk of X of this size, right? X equals tl.load, and we're going to start with our X pointer. That tells the actual place in memory to start, then plus offsets. So we are taking, this is a pointer to the spot in memory that has the first entry of X, right? And then when you say plus offsets, now you have a pointer to all the 64 first elements, or 64 in the example case. As I said earlier, our actual block size is 1024. So really it's grabbing the first 1024 entries in the X tensor, assuming you have PID 0. PID 1 would be grabbing the next 1024 entries, right? And PID 2 would be grabbing the 1024 entries after that, right? And same thing for Y. Y equals tl dot load, and it just has y pointer plus offsets, right? So now we have in our actual SRAM these two little blocks, these two little chunks of actual full tensor. So they're a very small subset of the full tensor that we're going to manipulate now, and they are of shape, block size, right? Because of this piece right here. And what we do, really simple, our outputs, this is also a chunk of our final output. It's not the actual full tensor. This is what we're going to just call it for a second. Output equals x plus y. Really simple. Triton actually has all of the built-in operations in there for you. You don't have to like define from scratch exponentials and additions and divisions or anything like that. Even blockwise matmul, meaning later for our matmul kernel, we'll be grabbing sections, little chunks, little blocks of the actual tensors, and those little blocks can themselves have a matmul done on them. We don't have to actually define matmul or anything, right? Output is x plus y, and then write data back to DRAM, right? Now that our calculation has been done on SRAM, we're going to write that data back to DRAM with tl.store output pointer plus offsets, right? And that writes the actual data back to DRAM. So as you can see, conceptually very simple. We're just having to be aware of what the actual GPU does in the process of moving from DRAM to SRAM. However, we haven't actioned the full thing yet. This kernel has a pretty glaring bug in the sense of, remember earlier where I said, well, there's a total number of elements in the actual input tensors, right? And we also have our block size. So my example earlier was 4,096 elements and a block size of 1024. What if our number of elements was not a clean multiple of block size? What if we had 4,097 elements, right? If we did that, if we had that, then our actual launch grid would have 5, not 4 different kernels being called because of our ceiling division function. And that last kernel being called, the 5th one, would only have one entry to work on, and yet it would be told that you have 1,024 block size, right? What you got to do is you want to make sure that you are not using those extra 1,023 entries. Reason being, Triton's not very smart, or like GPU is not very smart. If you don't account for this, then they will just load 1,023 of whatever the next entries in memory happen to be. Like they will just load random values that whatever was there in memory, and they will start doing the math, the addition on those, which would not be good, because then that would mean they would load those 1,023 entries, they would do the math on them, and then they would also write 1,023 extra entries back onto DRAM that would be overwriting who the heck knows what, right? They don't actually, like, it has no actual awareness of the limits of the tensor, of this actual output tensor. What we do, though, is we create a mask, right? And our mask is just, we take our offsets array and we say wherever it is less than n elements, right? So n elements is 4,097. So on that final offsets, which is the, like, what would that be? That would be 4,097 up to 5,000 something, right? Only the first entry of offsets, this actual comparison will be true. Therefore, what you got is a mask of one true value and a bunch of false values. Or if we had a different value of 4,098 or something like that, would give a different number of trues and falses. This mask can tell us, okay, we actually only want to load and do math on and write to any values for which this is true, right? And we can add that to our load statement and say, hey, actually don't load this entire memory pointer. Don't load this entire thing. Instead, we're going to say mask equals mask. And you don't always have to do this part, but because there's a default value of just nothing, but we can do it here is other equals none, just to demonstrate. Later, we'll choose different values for other. What other means is, okay, for anything that was masked out, for any entries we don't actually want to use, we are going to just put nothing there. Other equals none, right? We could have instead put 0.0 there. We would have a bunch of zeros where the masked out stuff goes. But here we'll just do none. And what happens now is for that last PID, for that last program where it had the one single entry, right? Our 5th PID, where it had that one extra entry, we're gonna have a mask of a single one, then a bunch of zeros, and all those all those falses, all those zeros will get put just nothing in there. They will not actually read those memory pointers, and they will instead just be nothing. We do the same thing for y. Go ahead and copy and paste this onto y. Again, we don't actually need to do the other equals none thing in this case because it defaults to none, but in the future, you may want to choose different values instead of none. And here it does math, and none plus none equals none, right? So not a huge issue. And then when we write back later, we also write with a mask saying, hey, I know these pointers go off all the way to 5,000 something, but actually use this mask to make sure we only write the 4097th one row, right? We don't actually want to write everything, just some stuff. And right there, that is our kernel, which hopefully, if I haven't messed up and put any bugs in here, this should run. Let's go ahead and save it. And then let's clear out this. And then I need to actually CD into the correct place. All right, we are CD'd in. Oops, I forgot to actually call the test. So let's call that test function. Let's call it twice, actually. Let's call it once with our simple 4096. Let's do another time again, just to demonstrate our 4097, because 4097 is not an interval and not a multiple, of 1024, our block size. And then here's another big number that's also not a multiple of block size, right? 98,000 something or other. And if we go ahead and run these, oops, I almost forgot. So for tl.store earlier, I only gave it the memory locations, the pointers to where it should write. I didn't actually say what it should write to those pointers. So outputs, then mask equals mask, right? So I forgot this little piece right here, the actual value that we want to write to memory. Output, of course, right? One more bug I found here is that in the wrapper function, I accidentally wrote down out, not output. But anyways, after all that, finally, you can see here, passed, 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 meaning that's our test passed in that our Triton kernel add matched the values exactly of PyTorch's own math, right? Perfect. Now, the final thing we want to do is actually test and see how fast is this kernel, right? Because the point is speed. If you're writing kernels but they're slow, there's no point. Just go use PyTorch, right? You want to beat PyTorch or at least match it. For this tutorial and for the next 2 or 3, I think we're going to match PyTorch's speed. But for the ending tutorials, we're going to actually surpass PyTorch and do something even faster, right? What we're going to do is create an actual benchmark. And luckily, Triton already has built-in benchmarking for us, right? It's got a whole system for it. So what we do is we start off with Triton.testing.performance report, perf report. And then what we need is a bunch of config files for our actual benchmark. So Triton.testing.benchmark. These are built-in parts of Triton that I don't understand very well. You don't really have to. You just have to know how to use them. Sorry. And then here we say xnames equals size, right? So this is the actual x-axis of our eventual graph that we're going to get. It's going to show us the actual speed. This is the different sizes of the input vector we want to test. It's going to start off with a very small input vector and then test a larger and larger one. You want to test many different sizes of the vectors, both to be statistically significant and to get an idea of how your kernel performs over a different range of matrix sizes and tensor sizes and whatnot, right? And our variable name here in this case is size, then x vals. So what are the actual values we want to give to size, right? We're going to say 2 to the power of I for I in range 12, 28, 1. These values are sensitive to how much actual DRAM, how much GPU memory you have. On here, I am on a 4060 Ti, and that has 16 gigabytes of DRAM. So if you have that much DRAM, you should be fine. But if you find that you get errors involving too much DRAM being allocated, then you can go ahead and change 28 to like 24 or 20 or something, right? Next we do x log equals true. This just makes the x-axis logarithmic, pretty to look at. I know this course requires as a prereq certain math stuff. I'm going to assume you know what a logarithmic scale of a actual graph means for that. And then line arg equals provider. So this is the actual input argument kind of variable name we're going to see in a bit. We'll explain that a little bit later. And then line values. So the different providers, aka different functions going into provider that we're going to have are either Triton or PyTorch, right? And then line names. This is just a pretty thing so that in the actual legend of the graph, it's going to have prettier names that are more descriptive, which in this case isn't actually very different. I'm going to just capitalize them and call it a day, but you might want to have far more descriptive line names. Oops, I meant to equal sign here. And then styles, this actually uses matplotlib under the hood. So let's say the first one, Triton, can be blue and have dashed lines, I suppose, or a solid line, maybe, for what that is. And then the second one can be green. So PyTorch will be a green line. Also, I think that's a solid line. And then Y label, what's the actual Y axis called? And you have to figure out what you're going to call this based off what you're measuring your benchmark on. Benchmarks can be measured either based off gigabytes per second or teraflops, or maybe if something else you want to measure. Most of the time, though, you want either gigabytes per second, as in read memory rate, or teraflops. Here in this function of addition, we do relatively few actual calculations, or relatively few actual flops, and we do a lot of memory reading and writing, right? We read from memory from DRAM once here, then a second time here, then we write to it once here for 3 total memory operations, whereas we only actually do 1 floating point operation, right? So we're going to measure in gigabytes per second in memory operations because that's the limiting factor here of this kernel. Other kernels such as, I believe, Matmul and Flash Attention have way more flops than they do memory operations, so we'll measure them later in teraflops in future lessons. And then our plot name is, let's call it vector add performance, right? And then this final thing, args, we're going to use this later. We're not going to use it right now. Even if you're not using it, you still have to actually put it right there and give it an empty dictionary. So we'll see how that gets used later for a future benchmark in a different lesson. Now define benchmark. This is the actual benchmark we're going to run. Size. Remember earlier, size is just the total number of entries in our input vectors. And so these will be the actual values for size. So benchmark is going to have size and provider, right? So this, we are telling, given that this input is provider and that this line arg is provider, we are telling the benchmarking, built-in benchmarking of Triton, hey, that the different things to benchmark are going to be different providers, right? And their values are going to be either Triton or Torch, right? So first we create input data, and then this is pretty similar to earlier. I'm going to just copy and paste them in. X and Y are normal distribution input data. I did specify data type here. In this kernel, we didn't actually do any data type stuff at all in here. It's all just takes whatever data type you give it. And Triton does support most, but not all, I believe, PyTorch data types. That if you're doing float 16, float 32, and I believe also BF, whatever you call it, bfloat 16, those all should work. Maybe not bfloat. I haven't actually used bfloat with Triton yet. Now, when we run our benchmark, it's going to run many times, and we want to know when we run it many times, we want to know which values to actually print out, right? So we're going to say quantiles equals 0.5, meaning give us the median benchmark run, as well as, I'm going to say 0.05. So give us the, if you were to run it 100 times, what is the 5th slowest benchmark run? And then 0.95, if you ran it 100 times, what is the 5th fastest benchmark run? Because there's some variability in here, right? Like it's not perfectly the same every single time. It's relatively close though. And then we need to actually define which provider this individual call of benchmark is going to actually use, and what it should do accordingly. So if provider equals torch, then we say milliseconds, or minimum milliseconds, aka our 0.05 value, and maximum milliseconds, aka our 0.95 percentile value, equals triton.testing.doBench. And the function that goes in, we're going to turn it into a function rather than its actual output is x plus y. This is now an inline function. And then we're going to say quantiles equals quantiles, right? And if provider equals Triton, here we're going to call our own. And so it's ms, min ms, oh, I have a mis here, that's wrong. Max ms equals Triton.testing.do bench lambda, and then the function we're going to give it is add x and y. That's our Triton wrapper we made earlier. And same thing with quantiles, right? Now, this gives us milliseconds, aka time it took to run those functions and the 5th, 50th, and 95th percentile for that amount of time, right? For milliseconds. What we actually want is gigabytes per second. So we have total time run. We need to know, okay, well, how many gigabytes of actual memory read and write did we do? And therefore, gigabytes per second once we account for milliseconds, right? So we say gigabytes per second is going to be an inline lambda function, right? It takes as input milliseconds. It's going to take as input one of these three values, ms, min ms, and max ms, right? It's going to be 3. 3 is our number of memory operations, right? So, oh, this should be a colon. 3 is our number of memory operations. So we read from memory once here, or on x.tl.load. Then we read from memory a second time here. That's 2 total. Then we wrote back to memory once here for tl.store. That's 3 total memory operations times x.numal. So we did 3 memory operations, and each of those operations involved this number of elements of actual memory, like of actual entries, of actual floating point numbers. And then we need x.element size. We chose float 32, but if we had chosen float 16, it would have been half the actual size. We want an accurate reading of our total memory operation. So this gives us the size per element, total number of elements, and total number of times that we did that many elements of reading, writing, right? And then we multiply by 1e negative 9. That converts the raw bytes, this is in bytes, over to gigabytes, right? And then we divide by our milliseconds, but first we convert milliseconds to seconds using this 1e negative 3. And then we return as our final values, our answer of our individual benchmark run. Our benchmark gets run for each provider, right? And for each size. Size is being defined here earlier. For this benchmark run, we return gigabytes per second of ms and of max ms and of min ms. Side note, I believe Triton expects you to return the primary, the ms here, then the upper value of your confidence interval here and the lower value of confidence interval right here. And yet for some reason, when it gives you those values, it's in a different order. It's min before max. That's odd to me. I'm not sure why that's the case. Maybe I just made a typo one time that's actually wrong. But it's odd to me that Triton has a couple inconsistencies in its actual notation for things that I'm not very fond of, but oh well. So this should now be our full benchmark. And when we go to run our script, we can say, okay, I don't want to run it every time because maybe I'm just testing and not actually running the benchmark every single time, because benchmarks can take quite a while sometimes. They can be very, very slow, especially in later lessons. And so we do import system, and then this lets us just do actual input argument. So if length of system.argv is greater than 1 and sys.argv1, so this just checks to see if we actually have any input arguments, and then if that input argument equals -- benchmark, then we call benchmark.run save path equals, we're going to say save it to this location, so period, and print data equals, let's say true. Why not? It doesn't really matter right here, right? But this will say we can now optionally run our benchmark. So let's go see if we can get this to run. Let's clear out of all that. And then, so we call Python and our file name is 1. In this case, I think in my tutorials, actual Git repo, it's going to be like, like a vector addition or something. Then we say -- benchmark. And are there any errors? So we named something incorrectly. Didn't expect live vals. It's line vals, might be. Let's try it again. Oh, here as well, styles, not style. Oh, and I haven't installed everything. Real quick, there should be a requirements file in the actual GitHub repo. I'm gonna just do it manually. Pip install, just make sure we get everything. NumPy, matplotlib, pandas, pytest. I think later videos I'm recording today are gonna use all of those. And Triton and PyTorch already work, so that should be good enough for us. Okay. Now we can try again, just passed all of our tests. It always runs those. And it is now in the background running our actual, oh, it already finished our actual benchmark. And here we can see the values. Let's, instead of looking at the values, let's check an actual image of what this looks like. And we can see here, blue is Triton, green is PyTorch. They are roughly the same speed. I see a little edge in Triton in a tiny few cases, but it's not very significant at all. It's the same thing, right? So we can see on the x-axis is the actual size of our input vectors. Y-axis is gigabytes per second that are being read and written to, and they are pretty well aligned. With a kernel like this that's so damn simple, you're really not going to find from just doing this any speed up over speed up over PyTorch. It's more so when you get into complicated kernels and kernels that PyTorch doesn't even actually specifically implement, where you can start fusing things together and doing things more efficiently. But that is for our next lesson. I hope you all enjoyed. As always, check out the pinned comment for any corrections that didn't actually come in the video. That should have any like, did I mess up somewhere? It'll all be listed right there. And link in description to the GitHub repo as always. But yeah, end of video.